Hi, everybody. Welcome back to Dave's Math Channel. This is my continuing feature on the Math Lovers book. I haven't advertised it in a while, might as well do that. So it's a 3-volume series that's available on Amazon.com, both in Kindle and in paperback. And I forget the price, but there's 3 volumes which you can purchase separately or together. And you can search for it either using my name, David Tare, or the Math Lovers book. And I do recommend this series. But if you don't want to spend the money, you could keep watching my series on this channel, which I'll probably do for another year or so. I'm about 2/3 of the way through volume one. Today's my last video on chapter 7 of volume 1, which is on logic. And this is a very important topic in logic, namely Gödel's incompleteness theorems. They were discovered by a very famous German mathematician named Kurt Gödel in 1931, first proven by him then. I'll just tell you what they say. I'm not going to try to prove them. The proofs are very, very complicated, by the way. I have gone through the proof of Gödel's first incompleteness theorem, but I think it's like hundreds of lines long. But basically, first I have to tell you what the theorems say. So the first theorem says that mathematics is incomplete. And not just mathematics, but any rich enough logical system. Uh, it could be a branch of mathematics like number theory or geometry. And what do I mean when I say it's incomplete? Well, what I mean is that you know how you can prove everything and disprove everything in math. Every mathematical statement. I mean, that's what people used to think. In the 19th century, there was a program that was initiated by a couple mathematicians. Russell, he was a pretty famous set theorist as well. Another one named Whitehead. They tried to prove, or they tried to axiomatize all mathematics. What that would have meant is that any mathematical statement you can write down or state, like you know, I mean, there's just simple examples like every triangle on a plane, the angles add up to 180 degrees. That's something you can easily prove within Euclidean geometry. Or it could be something a lot more complicated, like the Banach-Tarski paradox, which says that you can partition a solid sphere into and repartition in a way that you get two exact copies of the original sphere. Very, very counterintuitive result, but it is provable. It is a theorem. And so, what Russell and Whitehead wanted to prove was that anything you could say in math, you could either prove or disprove. It's either true or false. Everything in the world is either true or false, presumably. So, you could just start with any statement about math as long as you could define all your items in your model. And then what Russell Whitehead thought, and a lot of other mathematicians thought this as well, was that there should be a way to prove it. If it's true, you should be able to prove it mathematically. If it's false, you should be able to disprove it. But what Kurt Gödel proved was that their program was impossible. There actually are statements in math that are unprovable. They're true statements about numbers, for instance, in number theory, that are unprovable. It doesn't exist a proof. Um, and pretty counterintuitive result. And a consequence of that is second incompleteness theorem says that no mathematical system can prove its own consistency. So we would like math to be consistent, if nothing else. If it was inconsistent, you might as well throw it out the window because then you can prove, you get contradictions, and you don't want to have any system of knowledge involving contradictions. I don't think you can't have something be true and false at the same time. As far as I know, if you did, the world would be a pretty messed up place. But that's not what Gödel's first incompleteness theorem says. It just says that math is incomplete. I think the way you prove it is you get a contradiction. If you assume that it's complete, then you're forced to conclude that it's inconsistent, and that you don't want. So therefore, we conclude that it's incomplete. But the second theorem says a little bit more. It says that no system like number theory or Euclidean geometry, you can't prove the consistency. So for all we know, it might not work. I mean, yeah, that's an even more negative result, But they're very counterintuitive results, but usually, math works fine. I mean, usually you have to deal with very, very complicated, conjectures that are unprovable. And one thing that's kind of weird about this is you might think, well, maybe some of the most famous problems mathematicians are working on today, like I think the most famous unsolved math problem is the Riemann hypothesis. This was proposed by, Bernhard Riemann, a very famous German mathematician in the mid 19th century. Nobody's been able to prove it, although most mathematicians believe it's true. And I can think of a lot of other examples too, like the Goldbach's conjecture that every even number greater than two you can write as a sum of two primes. Almost everybody believes that's true, but nobody's been able to prove it yet. That's even an older unsolved problem dating back from the late 17th century. So, for all we know, maybe some of these results are unprovable. I think we actually do know some mathematical results that are unprovable. I think the most famous case of that is the parallel postulate from Euclidean geometry. For I think almost 2,000 years, mathematicians were trying to prove it. It was put in Euclidean geometry as an axiom, but it was kind of unsatisfying. A lot of mathematicians want to be able to prove it, and then it turned out, by the 19th century, that you can't prove it or disprove it. As a matter of fact, there are geometries, plane geometry, it's true, but there's curved geometries like hyperbolic geometry, which was discovered by Lobachevsky in the mid 19th century, and then there was spherical geometry discovered by Riemann, the same Riemann I mentioned earlier. And in both of those geometries, the parallel postulate fails. Um, anyway, there's a lot of other results like that in math. There's a lot of things that are unprovable within your system. I mean, it's kind of weird, and there aren't that many that I know of anyway. But anyway, that's kind of what Gödel's incompleteness theorems say. When I first learned about this, I was really taken aback. I mean, I was thinking to myself, no way, that can't be true. But, actually, I saw an explanation that made a lot of sense to me. I think this is by, a famous kind of math popularizer named Rudy Rucker. I read one of his books where he gave a pretty good explanation, I thought, for Gödel's incompleteness theorem, the first one. He said that math is finite by definition. If you start with any system, like Euclid's axiom, Euclidean geometry, it's a finite system because it's completely defined by, whatever concepts you put in a theorem as well as the axioms. That's all that goes in the theorem. That's a finite amount of information. And information can't be created or destroyed. This is a well-known result. So since only a finite amount of information went into your model, only a finite amount can come out. That means that there have to be things that are unprovable because you can state an infinite amount of possible things, but you can only prove a finite amount because you can only get out as much information as you put in. I think that's my favorite proof, intuitive proof of Gödel's incompleteness theorem. But if you want to learn more about this, here's a book I would really highly recommend. I bought this book just shortly after it came out. This is by a very famous physicist named Douglas Hofstadter. As a matter of fact, I believe he won a Nobel Prize for high energy physics. And he's written a couple of really excellent books. I think this is the first book, or at least the first really popular book he wrote. It's called Gödel Escher Bach, subtitled Eternal Golden Braid. And he mostly talks about Gödel's incompleteness theorem. It's a long book. It's about, I think, 600 pages, but he has all these, it's kind of amusing. He has all these anecdotes in it between Achilles and the tortoise, and, he talks about things like Zeno's paradoxes, and it's a very entertaining book, but he kind of gives you an intuitive idea of why Gödel's incompleteness theorem is true. And I think by the time you finish reading your book, you should be convinced that it is. And you probably learn a lot more math as well. He talks a lot about recursion and math. You kind of at the heart of Gödel's incompleteness theorem is this thing called recursion. When things refer to themselves, you got a lot of weird results. Sometimes you get paradoxes, at least things that seem like paradoxes when you have mathematical concepts that refer back to themselves. Um, since I already started talking about this, I might as well kind of give you a glimpse of why Gödel's incompleteness theorem is true. In number theory is rich enough to state things like um, you could have a theorem that says, or you could have a mathematical statement that says I am not a theorem. It talks about itself. And could you prove that theorem? I mean, if you did, you get a contradiction, right? Because the statement says I'm not a theorem. So if you proved it, it would be a theorem. It would be a theorem that says it's not a theorem. And you can't have that because that's a contradiction. So that is an example of a sentence, a mathematical statement that is impossible to prove or disprove. You could disprove that; it would be true, right? I mean, if you could prove that I'm not a theorem is false, well, it says I'm not a theorem, so it would be true, right? So that's kind of at the heart of Gödel's incompleteness theorem. And I do recommend this book. I read it when it was almost hot off the press. It was bought in 1970. It was written in 1979 and published that year. And I think I either bought it the same year or maybe the next year. I remember I was working at a really good museum in San Francisco called the Exploratorium, hands-on science museum. I was an explainer there for a couple summers, and I remember they had it in their bookstore, and I couldn't resist it. I kind of thumbed through it, and I thought this is a really great book, and I bought it. And one of my favorite math books I've ever read. So I do recommend this book if you want to learn more about Gödel's incompleteness theorem. Anyway, that completes my video for today. That also completes chapter 7 of volume 1. Next time I'll start talking about computation, how computers work, basically. And, it's a very closely related topic because at the heart of every computer is logic. Computers work with logic. So we use a lot of logic when we talk about computers. But anyway, that concludes my video for today. So thank you for watching. Long live math, and I'll see you guys next time. Bye.